What if I told you IPv6 secretly fixed the biggest problems in networking? While IPv4 headers were bloated and inefficient, IPv6 streamlined everything, but added powerful new features like NDP that make ARP look ancient. In this video, I'll tear apart IPv6 headers, reveal how ICMP-v6 is smarter than its predecessor, and show you the magic behind stateless auto-configuration. Stick around. By the end, you'll see why IPv6 isn't just the future, it's the upgrade your network desperately needs. Comparison of IPv4 and IPv6 headers. An IPv6 header is larger in size than an IPv4, because the addresses in version 6 are much longer. On the other hand, it has been cleaned up because it contains much fewer fields. Here is an IPv4 header. It contains, in all, 14 fields. The options field at the very bottom is optional, and the padding field, right next to it, allows you to fill in the option field so that the header is 32 bits in total. As you can see, the IPv4 header is 20 bytes. The 7 fields that are represented in red no longer exist in IPv6. The field that corresponds to the header length has been removed because the IPv4 header has a variable length, while in IPv6, it is fixed at 40 bytes and is not variable. The fields that are used for fragmentation no longer exist either, because in IPv6, routers no longer handle fragmentation. It is the hosts who have this responsibility. They are the ones who take care of the fragmentation if the maximum size of the package has been exceeded. The checksum field that detects transfer errors is removed because in IPv6, it is the data link layer that performs this check. And the options and padding fields are no longer useful in IPv6. As for the other fields, they are almost unchanged in IPv6. And here is the representation of an IPv6 header. Here, we can see that it fits on 40 bytes instead of 20 for IPv4. So, we could ask, how come there are fewer fields and that it is 2 times bigger? Well, it's because of the IPv6 addresses in the source and destination fields, which are 4 times larger than in IPv4 because they are written in 128 bits instead of 32. The IPv6 header contains 8 fields. The version field is simply the version of the protocol, 6 for IPv6 and 4 for IPv4. The traffic class field is similar to the TOS field of IPv4. It allows you to mark a priority on outgoing packets. The new flow label field is used to mark flows with different values so that they can be differentiated on the network. Very useful for routers when they need to deal with queues. Payload field corresponds to the total length field in IPv4. The next header allows you to identify the next header. The hop limit indicates the maximum number of hops that an IP packet can make. It starts at 245, and every time the packet passes through a router, well, that number is decremented. This means that an IPv6 packet can make a maximum of 254 hops before it is dropped. This prevents packets from circulating indefinitely if there is a routing error. And the source address field identifies the source of the packet. And destination address for the destination of the package. Now let's take a detailed look at the composition of an ICMP-v6 package. It does the same thing as in IPv4. That is to say that it also allows you to do diagnostic tests and report problems, but with more additional features. The type field identifies the ICMP message type. The code field gives details about the type of message. The checksum field represents the validity of the packet at layer 3. And the data field contains the diagnostic information, which is sent to the receiver, to inform the receiver that this is an IPv6 packet. The next header field in the header will have a value set to 56. Now let's talk about the NDP protocol. It is a protocol used in IPv6, which works at layer 3 and which makes it possible to discover these neighbors of proximity. That is to say, from the same link. The IPv6 NDP provides services very similar to ARP in IPv4, with some improvements more, such as the ability to detect inaccessible systems. It works with 5 types of IPv6 packets. The solicitation message allows a host to ask all routers present to send them an advertisement, so that they can save it in their neighbor list. The announcement message allows the router to warn its presence to all the nodes that are connected to it. It is a packet that periodically responds to the solicitation message. The neighbor's solicitation message has 3 functions. First, it allows a node to determine the IP of its recipient. This function is identical to the IPv4 ARP protocol. It also allows you to check if the equipment is accessible. And finally, during the auto-configuration of the IP address, he will be able to check if it is not used by his neighbors. The neighbor's announcement message is used to reply to the previous message, the neighbor's requests. And the 137 type message allows routers to signal to hosts that a better path exists for a destination. Stateless auto-configuration, SLAAC. To finish this course, we're going to talk about stateless auto-configuration, which is one of the big new features of IPv6. It allows each device on the network to automatically assign itself an IPv6 address based on the information provided by the router in these announcement messages. To do this, it will retrieve the prefix of the IPv6 address, obtain these, to combine it with the MAC address of its own interface with the EUI64 method. That is, he's going to add ff.fe in the middle of his MAC address. The IPv6 address autoconfig command enables stateless auto-configuration on router interfaces. And if we add the default, the router will designate itself as the default gateway for this link.